chapter of thermochemistry is the one on the very bottom of the screen here, finding the bond association, using bond association energies to calculate a standard enthalpy of a chemical reaction. To continue these thermochemical calculations, we're going to be using bond dissociation energy. The amount of energy that has to be supplied to break a chemical bond, it always requires energy, to break a bond in an isolated molecule in a gaseous state. It's hypothetical in the way it sounds in many cases, but it's the amount of energy released when the bond forms. So you have to supply energy to break the bond, and when the bond is formed, you release energies, two different things. So it's a standard enthalpy change for the corresponding bond-breaking reactions. That's what bond dissociation energies are. How do we get them? We look in a chart. There is a table from your text of average bond dissociation energies. The letter they use for this is D. D for dissociation. That sounds fair. And it's kilojoules per mole, always per mole. Pay attention to moles. And notice that all of the bond energies are positive. It always takes energy to break a bond. But in making a bond, the reaction energy would be reverse. There are single bonds all over the place in most of this chart, but at the bottom we have different values for multiple bonds. So if you have carbon-carbon, carbon-oxygen, or nitrogen with multiple bonds, you'll have to look on that part of the chart for the proper value. Okay, so let's see how we would use this, apply this to an example. So if you take hydrogen plus chlorine to make HCl, hydrogen chloride gas, we can calculate the enthalpy change for that process if we can do it using bond dissociation energies. What do? We take the energy of the bonds of the reactants and subtract from that the energies of the bonds of the products. Why do we subtract the bonds of the products? Because we're going to be we're thinking about breaking the bonds that you have to break are the ones that we're going to take with values as shown. We'll break those bonds, and we will release energy in forming the product, and we're making bonds. And so using those values as the opposite sign of what's in the chart is going to be the exothermic processes, exothermic, and that's why we're going to use them in their negative sense. And the breaking bonds is endothermic, and we will add those together. So for the overall process, we will take the bond energy for the hydrogen bond, H2, and the bond in Cl2. Subtract from that, oh, here we go, stoichiometry, 2 times the bond energy for HCl. So from the chart, if you have the numbers where you can refer to them in your text, it's 436 kilojoules per mole for hydrogen, and we'll just need one of those. And 1 times the chlorine-chlorine bond, which is 243. And from that, we subtract twice the value of the HCl bond energy. And so again, it's arithmetic. Put it together carefully. We come up with a value. It's minus 185 kilojoules for this reaction of making 2 moles of HCl for 2 moles. Be careful that you see what it is in this reaction. All right, let's use this as an example as we think about how we can do this in other options. We have one here that's kind of a puzzle at first. Which reaction shown is the most exothermic and by how much? So first we have to figure out how in the world do we have 2 choices here? And this one puzzled me at first, but then I had to realize what they were forcing us to do. We have to determine which reaction has a correct energy in the products. So forming these products is generally going to release energy. But if that HF reaction has 34 or 531 kilojoules is problem number 1 versus the hydrogen plus chlorine reaction making HCl is at 447 or 179. Well, we just did the one for HCl, so let's flip back to the previous slide. We did this one. 185 is the number they have here. Well, that's using different numbers than are shown on the next slide. So we're probably going to be close to this. It's going to be slightly different in their values. Let's figure them out. So the hydrogen, the bond dissociation energy for the HCl reaction for 2HCl is going to be what? Well, we should have to use the energy of the reactants bond energies of the reactants minus the bond energies of the products. And so which are they? It's going to be the hydrogen bond, which is HH in this example. Oh, the numbers are a little different on the previous slide, that's why. For hydrogen bond, and the chlorine bond is the 243. We'll put those in. Subtract from that the energies of the bonds of the products. In this case, it is HCl, which is shown to be 431. And we have to take this one times 2 because it's twice in this reaction. Double check, make sure our numbers come out. Oh, I'm sorry, I was writing the wrong way. Let's put it in the other way. The products are the HCl, but 2 HCl bonds that we have to account for. So hydrogen is 440. Chlorine, we'll add that, is the 243. Subtract from that 2 times the HCl value, so hydrogen-chlorine bond, I'll put the number in this time, 431, and try not to run out of space. We will put this together, and we should get an answer, and in this, using these values, I get minus 179, close to the previous page, but they're slightly different bond energies reported in this particular example. Now, what about, so this one is correct of these 2 choices, but we want to see which one is most exothermic. So let's do the HF. For the HF reaction, making 2 HF, same idea. Now we've done it once, the second example is a lot easier. So the bond energies of the reactants, and subtract from that the bond energies of the products. So the reactants, what are they this time? The HF reaction is going to be 2 HH bond, breaking apart a hydrogen, breaking apart a fluorine. Those bond energies, subtract from that, always pay attention to your signs, it'll get you in trouble if you don't, 2 times the HF bond. All right, so if the hydrogen bond is going to be 440, still same thing, and the FF bond, look over there on the right, is 159. Subtract from that 2 times the HF bond, which is apparently 565. This is an exercise in reading numbers carefully. And if you put all that together carefully, if you get the same things that I do, this first value was 599, and this is 1130. The net reaction, or sum of the whole arithmetic exercise, is minus 531 kilojoules. These are all in kilojoules. And so this one was correct of these 2. So which process is most exothermic, making HF or making HCl? It turns out that the HF reaction is the most exothermic, is giving off the most heat. All right, one more example for this kind of thing with bond energies to give you an idea of how many ways you got to be careful. Let's figure out the bond dissociation energies, using them to get an estimation for the heat of formation of ethanol according to the reaction shown below. Ethanol, we've seen in an example or 2 sometimes, is shown at the left, CH3CH2OH is shown there on the bottom right with spheres and stuff. This is ethanol. And ethanol formation, reaction with oxygen to make oxygen and CO2 and water. So what are we doing here? Estimate the heat of formation of ethanol according to this reaction below. Well, guess what? This is a misstated question, as happens sometimes. This would be not formation, but combustion. If you're making CO2 and water, that's combustion. Okay, having said that, what are we doing? We're going to take the bond energies to put this together. The bond energies are shown in the pictorial representations at the right. And so we're going to take a sum of the heats of the dissociation energies for the reactants minus those of the products. Okay, ready, ready, ready? This takes a lot of careful effort. So let's think about it as we look at this together. I'm going to write them in a pictorial sense kind of first before I put in the numbers. So first of all, I'm just going to take apart the ethanol and find all of the bonds in the reactant. The reactant number 1 is ethanol. And if you look at it carefully, there's 1, 2, 3, 4, 5 places that we have a CH bond energy to use. There will also be a carbon-carbon bond energy. So let's put these together stepwise. 5 times the CH is 413. One carbon-carbon bond is the 348. And then what other bonds are we breaking? Let's see, what's else left here? Okay, there's this carbon and oxygen bond. And we are going to add that number into our tally. What other bond needs to break in that molecule to break all the bonds in the reactant? Well, it's the OH bond between O and H on the end, and that value is 463. What do we subtract then? Oh, but here is our pitfall. We have to have, oh, we didn't do it yet. We'll have to watch for it, and that is that we're going to break the bonds in oxygen, so that's the other part of the reactants. So let's take off the parenthesis and keep going. So 463 plus 3 times this oxygen O double bond O bond energy. And so that's 3 times 498. There is a very easy place. I'll be the first to tell you that I can miss that just as well as the next person. Subtract now the product bond. So what are the products? CO2 and water. Oh, good. Now we have to pay attention to coefficients. We'll get it right if we're careful. Be very careful. All right, so let's see. And the products then we have, so the bonds that we're breaking are CO2, and CO2 has 2 times 2 here. So it's times 2 again because there's 2 molecules, but there's 2 CO bonds. Because there's 1 here and 1 here. And that value is 4 then times 804. So, we're adding to that the other bonds in the product. So it's water. There's 3 of them. Oh, but where are they? Well, they're OH bonds, aren't they? They're OH bonds in water, but they're not shown in a water picture. Well, OH bond is already here. The OH bond is on the end of ethanol. So we're going to take 3 times the 463. So those are our bonds of our products. If you look at them carefully, those pieces will give us the sum of the bonds in the products. And if we put all the numbers together, and let me tell you, this is an arithmetic exercise that is not simple. Play it out on your calculator, give yourself a chance to try it, and notice how many ways you can make an error. But I ended up, after more than one reevaluation of my calculations, I got 1,264. All right, kilojoules per mole for this reaction, this combustion reaction. So we can do an estimate of a heat of combustion by using some bond dissociation energies. Kilojoules per mole. Isn't that an interesting long process? But again, watch coefficients, the stoichiometric coefficients. Otherwise, we will miss something. And like we used in this one, the 3 on oxygen, the 2 on CO2, and the 3 on water, because if we didn't include those, these were going to be incorrect all the way through. And write out all your steps. Write out all the steps. Watch the signs. Be careful with parentheses, because we got to be sure the right things are combined before they're subtracted. All right, these are challenging problems. We will not do all of the worst ones, but here's some examples of how they're done. I hope you find these helpful. Please ask more questions as needed. Good luck on your homework, and I'll see you in class.